Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are taking a deep dive into one of the most fundamental derivations in Unit 4, moving charges and magnetism. We're talking about the magnetic field on the axis of a circular current loop. Our mission is to make sure you understand the why behind that, that slightly complex formula so you can solve any problem that comes your way.
It's definitely a topic where students can get a bit lost in the geometry, I think.
Absolutely. They know the Biot-Savart law, but then applying it to a circle and all the vectors, it seems like a big jump.
A very big jump.
It does. So let's just, step away from the math for a moment. Let's start with a really simple question. If you pass a current through a perfectly circular wire, where does the magnetic field actually point? And how does all that curving current manage to create a field that is perfectly straight and focused at one spot?
That focusing part is the real mystery, isn't it? The current is constantly changing direction in the loop, but the field on the axis, it just points straight.
Exactly. And here's where it gets really fascinating. This entire concept. It's not just some random derivation. It is actually the building block for understanding magnetism itself. It's quite amazing to realize that the magnetism in, say, a bar magnet or a huge industrial electromagnet, it all originates from tiny, tiny current loops.
Yeah, tiny current loops. How?
Think about the orbital motion of an electron in an atom, or its intrinsic spin.
Okay.
Both of those act like microscopic current loops.
Wait, so an electron orbiting a nucleus is basically a tiny circular current.
Precisely. So if that tiny atomic loop behaves like a little magnet, then understanding our big macroscopic current loop is the first real step to understanding all of magnetism.
That really changes the perspective. This is not just an exam problem. It's the very source of the magnetic fields we use.
It's the foundation. Okay, so let's establish the core idea. The reason we always start with a circular loop is its perfect symmetry. And because of this high symmetry, the magnetic field is perfectly straight only along the central axis.
That's the line passing through the center, perpendicular to the loop, right?
Correct. And logically, the field is strongest right at the center of the loop.
That makes sense. At the center, you're closest to all parts of the current-carrying wire. But I'm still a bit fuzzy on how that symmetry forces the field to be straight everywhere on the axis, not just the center.
Good question. Okay, let's use an analogy to make this clear. Think of ripples in water.
Okay.
Imagine you are dropping millions of tiny stones into a lake, but you drop them all at the exact same time and only along a perfect circular path. That circle is our current loop.
So each stone creates its own little circular ripple.
Exactly. And all these ripples, which are like our magnetic field lines, they spread out and interfere with each other. But what happens right in the middle, along that central axis line?
They would all sort of add up.
They add up perfectly and constructively. They create one strong, focused wave that travels straight up or down the axis. Everywhere else, it's a complicated mess of interference. So let's build a mental image from that. The whole field pattern looks a bit like an umbrella or a mushroom.
A mushroom?
Yes. It's highly concentrated near the loop, that's the base, and then the field lines shoot straight out along the axis, that's the stalk, before curving around to form the cap.
Okay, I can see that. So the straightness is key.
And the key to that straightness is cancellation. For every tiny segment of current you look at on the loop,
there's another segment exactly on the opposite side, diametrically opposite.
Spot on. And each one creates a magnetic field, but they're sideways components.
They would be pointing in opposite directions.
Exactly. They're perfect mirror images, so they sum to zero, they cancel out.
And only the component pointing along the axis is left.
That's it. Only the axial component survives. This perfect cancellation happens for every single pair of opposite elements.
So the net field on the axis has to be purely axial.
Now you've got it. That's the power of symmetry. And it's what makes the derivation even possible. Okay, now that the concept is set, let's see how our textbooks, like NSERT, formally derive the formula. We have to start by applying the Biot-Savart law to one tiny element, dl. Could you read out the simplified formula for the magnitude of the field dB from that one element?
Okay, yes. From the text, it says, thus, dB equals mu naught upon 4 pi times I dl over x squared plus r squared.
Right. Now that looks a bit simpler than the full Biot-Savart law we learned, doesn't it?
It does. The original law has a vector cross product, d cross Hari, and an r cubed in the denominator.
Correct. So what happened here? Why is it simpler? This is a classic spot where marks are lost if you just memorize the formula without understanding the geometry.
Okay, so in the original law, the numerator is the magnitude of dl gauss r. That simplifies to all times r times sine theta.
And what does that angle theta between the vector dl and the vector r?
Well, dl is the current element, so it's tangential to the circle, and r is the vector from that element to the point P on the axis.
Imagine that triangle formed by the radius r, the axis distance x, and the hypotenuse r. The vector r is in the plane of that triangle.
And dl is perpendicular to that plane, so the angle must be 90 degrees.
Excellent. The angle is always 90 degrees, so what is sine of 90?
1.
Right, so the magnitude of dl cross r just becomes times ddl.
Ah, I see. So we have dl in the numerator and r cubed in the denominator. 1r cancels.
Leaving r squared in the denominator. And from Pythagoras' theorem, we know that r squared is just.
X squared plus r squared, that matches the formula perfectly.
Exactly. So that's step 1, getting the magnitude of dB. Now for step 2, using symmetry, which we already talked about. We only care about the axial component, dbx. How do we get that?
We'd need to multiply dB by the cosine of the angle between the dB vector and the axis. Let's call it angle theta. So dbx equals dB cos theta.
Correct. And here's the next beautiful simplification. That value, cos theta, is it different for different current elements and around the loop?
Since the point P is fixed and the radius r is fixed, the triangle shape is the same for every element dl. So the angle theta must be constant.
Perfect. It's a constant for the entire loop. Now, just looking at that right angle triangle, what is the value of cos theta?
Cosine is adjacent over hypotenuse. The adjacent side is the radius, r, the hypotenuse is r. So cos theta is r upon r.
Which is r upon the square root of r squares plus x squared.
Okay, so we have our expression for dB and we have our expression for cos theta.
We have all the pieces. The final step, step 3, is integration. We need to sum up all the dbx components from all the dl elements around the circle. But since everything else, mu naught I, rx, and even cos theta, is a constant.
We just need to integrate dl.
Correct. And what is the integral of dl over the entire circumference?
It's just the total length of the circumference, which is 2 pi r.
Exactly. So we just multiply everything together. When you substitute the expressions for dv and cos theta and simplify, it all combines beautifully. And this integration leads us directly to the final, absolutely crucial result. The magnetic field vector on the axis is B equals mu naught I r squared divided by 2 times r squared plus x squared to the power of 3 by 2.
That 3 by 2 power is the key signature.
It is. And the direction is along the axis. Now, let's look at the most common special case. The field exactly at the center of the loop.
At the center, the distance along the axis x would be 0.
Right. So what happens to the formula if you put x equals 0?
The denominator becomes 2 times r squared to the power of 3 by 2. The square and the half cancel, leaving r cubed. So 2r cubed.
And you have an r squared in the numerator.
So r squared cancels with 2 of the r's in r cubed, leaving just r in the denominator. So it's mu naught I upon 2r.
V center equals mu naught I upon 2r. That is an essential result. You must know it. This is the maximum field strength you can get from that loop. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROSSAM.com. Okay, let's quickly do a simple work example to see this in action. Imagine a coil, not just one loop, but a coil with n equals 100 turns.
Okay, 100 turns.
The radius r is 0.1 meters and the current I is 1 ampere. We want the field at the center.
So we use the simplified formula B equals mu naught I upon 2r, but we just multiply it by n, the number of turns.
Exactly. The effects just add up. So the calculation is 100 times mu naught, which is 4 pi into 10 to the minus 7 times 1 ampere divided by 2 times 0.1 meter.
Okay, so the 2 and the 4 cancel, leaving 2 pi. The 0.1 in the denominator is like multiplying by 10. So we have 100 times 10, that's 1,000. So it's 1,000 times 2 pi into 10 to the minus 7. That's 2 pi into 10 to the minus 4 Tesla.
Very good. And 2 pi is approximately 6.28. So about 6.28 into 10 to the minus 4 Tesla. This shows how wrapping more turns is a simple way to make a stronger electromagnet. Now for the deeper connection. This links this topic to the rest of physics. What happens very far away from the loop when x is much, much greater than r?
If x is much bigger than r, then in the denominator term, r squared plus x squared, we can pretty much ignore the r squared. It's too small.
Correct. The denominator becomes approximately 2 times x squared to the power of 3 by 2.
Which simplifies to 2x cubed.
Exactly. So the field B far away is proportional to 1 over x cubed.
Wait a minute. That 1 over x cubed dependence, that's very specific. I've seen that before.
It is the signature connection. It's identical to the axial electric field of an electric dipole.
So the current loop is the magnetic equivalent of an electric dipole.
Precisely. This 1 over x cubed relationship is the mathematical proof that a current loop is a fundamental magnetic dipole. This is why we can define a magnetic moment, M equals I times A, and model things like bar magnets. That connection is vital. Okay, let's talk about the silent killers, the common mistakes that cost marks. Silent killer number 1. Assuming the field is uniform inside the loop, many students confuse the single loop with a long solenoid.
Ah, so they think the field strength is constant everywhere inside the circle.
Yes, that is the wrong idea.
Yeah.
The correct idea is that for a single loop, the field is never uniform. It is strongest at the center, where equals 0, and it drops off immediately as you move away from the center.
It varies strongly.
Very strongly. Now, silent killer number 2, forgetting the direction constraints. Students draw the field lines as straight and perpendicular everywhere near the loop.
But we just established that the perfect cancellation of the sideways components only happens on the exact central axis.
That is the correct idea to remember. The field is purely axial only on that line. The moment you move even a millimeter off the axis, the cancellation is imperfect and the field lines start to curve. Remember the mushroom shape.
The stalk is straight, but the cap spreads out and curves.
Got it.
Okay, so to be safe, the strength is maximum only at the center and it's not uniform, and the field lines are perfectly straight only on the axis.
Spot on. If you remember that, you're safe. Now, let's lock this big formula into memory. We need a memory anchor. The formula is mu naught I r squared on top, divided by 2 times r squared plus x squared to the power of 3 by 2. The thing to remember is that denominator structure. Think of it as essential stuff on top current and radius squared. Below, you have the distance relationship, the combined distance squared raised to the power of 3 halves. That 32 power is the signature.
Right, the 32 power.
And for the direction, the physical gesture is the right-hand rule. Curl the fingers of your right hand in the direction the current is flowing in the loop.
And my thumb points in the direction of the magnetic field on the axis.
Exactly. Your thumb gives you the direction. It's that simple. All right, time for our final exam-safe summary bullets. Let's consolidate everything. First, the magnetic field on the axis of a circular current loop is always strongest at its center, where x equals 0, 0, and its strength is proportional to the current and the square of the radius. Second, because of the perfect symmetry of the loop, the components of the magnetic field that are perpendicular to the axis, they completely cancel out. This means the net field is entirely along the axis. And third, at large distances where x is much greater than r, the field strength drops very quickly, proportional to 1 over x cubed. This proves that the current loop behaves exactly like a magnetic dipole. And finally, here's a thought to take away with you. Since this whole thing shows that a current loop dipole is the fundamental source of magnetism, does this mean that magnetic monopoles, single north or south poles, simply cannot exist? Or are they just hiding from us? To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com. That is PROFSAM, right? Yes, PROFSAM.com. Thank you for joining us for this deep dive. Study well.